Test, test. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Good. Wonderful. All right. Good morning, everyone. Welcome once again to your favorite class in your favorite semester of your favorite year of your favorite degree. We will continue on with our discussion of classes today. I suppose, though, I should address sort of some of the I guess, I don't know. There were complaints. There were complaints in the survey that Mark put out about, you know, which questions you liked and which questions you didn't like. It's kind of funny. I thought that the one that was easy would end up being the hard one. Or I thought that the one, pardon me, the one I thought was easy, other people thought was hard, which was the Caesar cipher question. I thought that one was dead simple. And the one that I thought, oh, we're going to intimidate people, it was the calculus question. Because, you know, technically speaking, I don't think calculus is technically I don't think integrals are technically a prerequisite of this course, or in any of the prerequisite material of this course, although it's likely many of you will have seen them before, but I thought, you know, perhaps as long as we've got the formula in there, it's not going to be such an issue. So, and it turns out that that was correct. But I just wanted to address a couple of things that I saw from people that were basically along the lines of the questions on the test were, you know, different from the questions on the assignment. I.e., people felt that the assignments did not prepare them sufficiently well for the test. So this sort of comes down to a couple of, shall we say, pedagogical philosophies, which is a fancy way of saying that it was intentional. So the point of this course is to teach you how to program. Programming, in its essence, is not the sort of, it's very different from something like calculus, right? In calculus, you learn a procedure. You are tested on your ability to perform that procedure. This has been math class pretty much universally from, you know, very early in your education on forward. It's like you are not expected to derive the multiplication tables. You just have to memorize them. So what we're talking about now, that's fine insofar as it's applicable to math, very useful skill. But when you're programming, you're doing something different. When you're programming, you actually do have to come up with unique algorithms that you yourself have derived based on the particular situation that you're in. There's no set book of programs that you have to memorize and then repeat. If there was, then there would be no need for you to learn programming, because programmers would have already written a program that would already apply programs to the problems that you would need to apply programs to. programmers are pretty clever like that. So, yes, the questions on the test were not, were not variations on the assignment questions. There were also some complaints that apparently people were benchmarking the amount of time that an assignment should take them in this class by assignments 1 and 2, which are admittedly very easy. Which, all that's told me is that in subsequent offerings of this course, I should increase the difficulty of assignments 1 and 2 so that there's a little less whiplash, pardon me. So, yeah. This is what you do when you program, is you are thrust into novel mathematical situations, and you have to write a program that solves that problem. So fundamentally, this is a problem-solving course. If you have managed to get this far in the course without having come to that awareness, I am telling you right now, this is a problem-solving course, and the exam, in the same way, the exam is not going to be like minor variations on assignment problems. We're not trying to teach you specific programs. We are trying to teach you how to program, right? And in order to learn how to program, you need to, like, if you had fallen into this trap of imagining that the only questions I'm going to ask you are questions related to things you've already seen on the assignments, that is not going to be the case, essentially. However, I'm sure that many of you will have found on the test that while the questions themselves are can have a degree of novelty and uniqueness about them, they will still use or pertain to the topics as covered in lecture. So that's about the long and the short of it. Yeah. So, this is not memorization, right? We're not teaching you specific problems. We are teaching you logic. You must use logic to solve the problems, essentially. At any rate, that is, it might be a lot to expect during a summer course, but, it's a summer course. It's inextricable. It's an inextricable property of the fact that this is a summer course. So, I can't, it would be incorrect of me to, like, dial down the difficulty on a summer version of the course versus the regular semester course, because, like, for you to have taken this course, it should mean the same thing no matter when you took it, right? You should be educated to the same level regardless when you take this course. So essentially, I'm sticking to my guns. We're going to continue now with our discussion of classes. So, one thing that I noticed that I should have covered last time that I didn't was, which something people usually have some problems with, is this idea of self and other, which I'll go over that presently. And hopefully that'll be interesting to people. 8, yeah. There we go. So, we've used this construction a couple of times now, self and other. We use it, I used it in this add operator, which we applied to the person class, which essentially functions as a marriage operator. It establishes a relation of marriage between two person objects. And also, we see it in the point class during our definition of the distance between 2 points. You may notice, automatically, that I'm using this style of construction particularly when we are trying to write a function or write a method that relates two objects together, right? In the case of marriage, that is a relation. We are doing something with two people. In the case of the distance method, we are doing something with 2 points. So, self is one of those points. Other is the other point. Which may be reasonable. That sounds more straightforward than it is. So, remember that self, the first argument of any method, self, is self-referential. It is the object upon which the method has been called. So, in this case, where I'm printing p.distanceq, p is self. The rest of the arguments must be provided to the method when it's called. So, when we call distance and provide the point q, q becomes other. The equivalent, of course, this is, in some sense, syntactic sugar for the following, point.distance pq. So you can also pick the method out of the point class. You can refer directly to the class name rather than having to access it through a specific object. However, you're still having to provide the object which is considered self. So you don't get out of needing an object that way. But you can see how distance pq lines up much more in a much more one-to-one fashion with the arguments list as described by the method itself. Self is p, q is other. So, with respect to other, this is Python. So, specific types are not required in method or function declarations in Python. Personally, I find this annoying. I prefer languages which require you to say up front what your arguments are. However, this is the way that Python chooses to handle things. It makes it easier for beginners, I guess. I don't think it does, really, but all it does is confuse the matter. But, cue memes about the professor preferring every language to the language he's teaching. So, other is an object of the point class because within the context of the method's body, within the method itself, other is being used as a point class. So, other needs an X component, or it needs an X attribute, and it needs a Y attribute, and if it has both of those, then it will we can calculate the distance. If it doesn't have these, then you're going to get a runtime error when you try to execute that. An interesting corollary of this is that you don't actually require other to be of the point class so long as it has X and Y components. Fine, Sure. So if, for example, I had another class point3D, which, let's say just for the sake of argument, had an x, a y, and a z, self.z is equal to z0. If we were to create an object of the point3D class, and if we were to call distance with self being some object of the point class and other being some object of the point3D class, this would still work. But we would be calculating the strictly two-dimensional distance. So this reference to other would pick out self.x within the point3D class, and this reference to other.y would pick out the y attribute of an object of the point3D class. So we wouldn't run into an error because everything we're looking for is there. However, the problem I have with this is that it once again introduces these kinds of implicit properties or implicit assumptions about the data you're operating with. So if we expect self and other to be of the same class, it would be convenient to be able to specify that. But for all intents and purposes, in Python, I think it's possible to specify, maybe Mark, if he's listening, Mark might be able to correct me on this. Perhaps it's possible to designate data types for arguments in Python, but certainly the convention is not to. You'll notice that we haven't done that a single time in the slide so far. Is there a chance that we could have your exam mark replace part of your midterm mark if you do better on it? No. Is the exam going to be in the same format as the midterm? Yes. So that's a little bit more about self and other. Hopefully that explicates things slightly. So, methods are called using dot notation. We've talked about this already. We talked about overriding the string method yesterday. So that's fine. Here we go. So, we actually have a whole bunch of these double underscore methods which we can override that provide a whole bunch, a lot of different interesting functionalities to our method, to our classes. It allows us to use classes with Python's inbuilt syntax. While this is this is unnecessary, you know, it doesn't really matter. Like, you could just as easily have a method that performs marriage as use the plus operator. It's still a little bit cool, and there are ways in which you can reveal information using magic methods that you couldn't otherwise. For example, specifying something for string allows you to view details other than the object's memory address when you print it. So, we have a whole bunch of these guys. Another one, which is interesting, is underscore underscore EQ. So, it's also going to take self and other. So, EQ is programmer speak for equality. So, the operation that we're overloading in this particular instance is the double equal sign equality, our normal everyday equality operator that everybody should be well and truly familiar with at this point. So, the question at first becomes, what do we get if we try to equate 2 points which we would consider to be the same without having overloaded the equality operator? So let's print P is equal to R. We get false. So that's interesting, right? X is the same, Y is the same, but when we equate the two, we get false. What the heck? Well, let's see what's actually going on there. Well, I can tell you what's going on. If we had another one, say Z or X, and we try equating P and X, you'll find that that comes out true. So what equality is testing for by default is the memory address. Once again, it's the memory address of the objects rather than any of the information contained within them. So we are essentially testing. So equality tests by default over objects are tests for whether or not these two variables are aliases of each other. That can be useful. Don't get me wrong. That can be useful. But that's not what we mean by equality in this particular instance, right? We definitely mean, are these 2 points in space the same point in space? So, in order to make that more explicit, we fill out the equality method so that the equality operator links up to something that actually makes sense to us. So we then have to ask ourselves, what does it mean for 2 points in space to be the same point? We can break that down a little further. That means that the x component and the y component, the x components and the y components are the same. So return self.x is equal to other.x and self.y is equal to other.y. Notice that equality is perfectly valid to be used in this particular case because x and y are integers, or possibly floats. They are not objects of some class that we've defined, right? They are elements of some base data type, like int or float, which equality already has defined for it. So we can rely on the definition of equality within the definition of equality, which it seems like a circular argument, but it's not, because we're referring to definitions of equality elsewhere in the prelude, or elsewhere in the libraries that are provided by default for you to use in Python. Ta-ra. So if we include that definition, and we now attempt to print is P equal to R, test 1, test 2, bingo! Ah, that's interesting. Test 1 and test 2 are true. Huh. Oh, yeah, of course they would be. Heh. I'm like, huh. Is it still checking for the alias? No, of course not. Because, you know, essentially what this first test is now saying is p.x equal to p.x and is p.y equal to p.y? And the answer is, of course, yes. Obviously, right? So this will still pick up an alias because an alias will contain the same data as any other alias of itself, obviously. But it will now also test for distinct objects that happen to have the same data inside of them. Is instance. type hinting does exist, but is not 100% enforced by Python, as Mark says. Yes. So the operative term there is hinting. That should give you an idea of the degree to which Python is ideologically opposed to the idea that arguments should have types associated with them. Oi! Dynamic typing. I hate it. Static typing for the win. I tell you. Cool. So, you can overload equality. We can override this by providing an EQ method. So, the correct term for this is overriding, and the correct way to think about it is also overriding. The point class derives a definition of equality from the object class, which it inherits from, because everything inherits from object by default. Object is the most general thing. So when you perform equality comparison over a point class that does not have equality defined in it, the equality definition that your class will use is derived from the object, the definition of object. Now, it just so happens that the definition of equality that is derived from object compares the memory address of the two objects you're trying to compare. That's the default functionality. When you provide a definition for equality, you are overriding the derived function, or the derived method, right? So you're saying, all right, object, I see you have a definition for equality in there, but I don't care, man. I want my own definition. So when you define it inside of the point class, this will override, that's like the actual technical term, override, the definition of equality provided in the class that you are inheriting from, in the base class. So that's an important concept. Cool. So, we're going to get right into inheritance then. Let me see if we have any questions. So, with inheritance, you are being provided a way to include the stuff that's in other classes inside of your own class. So we've seen this a couple of times already. We've seen it with the exception class. We defined our own exception class by inheriting from Python's provided exception class. We didn't modify anything. If you remember this, this initial... There it is. If you remember this guy, we were inheriting from exception, and we were essentially relabeling the exception class so that we could use this new label to indicate, to be able to pattern match over new types of errors using try-except clauses. But we are in fact inheriting from exception. My error is the derived class, and exception is the base class. All of the contents of the base class are available to the derived class. The derived class derives everything that is contained within the base class. So, my error contains everything that is in exception. All the definitions in exception. I can probably show you that. Help exception. Yeah. So this is the class exception with all of the stuff that's in it. So we have a string, we override string, we override get attribute, for instance. And all of those things are available in my error. And the reason they're all available is because we have inherited from exception. So this is fine. And as I've noted a few times now, every class in Python inherits from object, which is the most general thing that provides you baseline definitions for a whole bunch of different things like equality and string conversion. Very often they won't do what you want them to. It's your responsibility to override these definitions so that they're useful, but they are provided nonetheless. So what we're going to do now is we're going to demonstrate how you can inherit classes that you yourself have written as well. So let me pull up this guy here. Yeah, okay. I'm going to make a new class here. Class. I was thinking about extending point3D, but probably better to keep it close to the sides. Point, so color point. Self, wait, no, that's not it. Sorry. So color point wants to include everything that is included in point. So color point inherits from point. We can now use color point in the same manner as a regular point. And in fact, if you remember, that business of me saying point3D would work because it has an x and a y component for equality comparison. You will see that color point, if I make p a color point, it still works for all of these equality tests. So right now we've just relabeled point, but as the name would imply, the point of our color point class is that we want to add an additional attribute which keeps track of a color. So that, if you're graphing these points, we have red points, blue points, yellow points, green points, etc., etc. So we should define an initializer. Should take self, x0, y0, and some color, not, and we'll do some stuff here. Well, so there are a couple of ways of going about this. You could do things the dumb way, just copy-paste stuff over. Copying and pasting. It's kind of weird. Sometimes copying and pasting is like the only thing you want to do in programming, and sometimes it's like never, never, never do it. It depends on whether you have a language construct that you can use to do the thing you're trying to do better. So this is fine and this would work. But we can also make reference to the initializer function of the point class within the initializer function of the color point class, provided x0 and y0. So we're invoking it like a function. It's got to also have self. It's not slef. Self. There we go. So point.init self x not y0. And self.color is equal to color 0. There we go. We can also provide a new method, call it darken, takes self and nothing else. Self.color is equal to dark concatenate with the name of the color. We're assuming color is a string. There we go. So, if we say that color point, if P is a color point and we make it red, and we call P.darken, print P.color, we get dark red. So, what this has allowed us to do is to add more specific definitions to the color point class without having disturbed the definitions that were already included in the point class. The point class has not changed. You can't, for example, if you were to call Q.darken, you will get an error. Point object has no attribute darken. So inheritance does not work the other way around, right? Things that, so derived classes come up with with different things, but nothing that goes on in a derived class will affect the base class. Everything that goes on in a base class will affect the derived class, but not the other way around. It's a one-way relationship. So, yeah, essentially. Yeah. The only reason Mark likes type hinting in Python is that GitHub can link the files together using the type hints. Oh, that's interesting. Well, there you go. Mark is such a font of wisdom. So, color point, the darken method, we add it to color point. So, in terms of top-level abstractions, ways to think about inheritance, you want to think about a thing that is inheriting from another thing as being a more specific type of that thing, right? When we inherit from point, we are saying that color point is a more specific type of point, right? So, yeah, color point is a more specific type of point. Cool. Let's see where we are in the slides. So, classes can be used to create objects and to define new classes by inheritance. All the definitions of the base class, or the parent class, are inherited as if they were copy-pasted. Copy-pasta. Inherited methods may need to be redefined, i.e. overwritten. The new method can refer to the inherited method using the class name and dot notation. So that's another thing. Right now, if we were to, if we use a quality comparison with P, we are comparing only the point in space. If we also want to have color factor into whether or not two points are equal to each other, we would need to override the overridden definition that exists inside the point class. So, return self.x equals other.x, and self.y equals other.y, and self.color equals other.color. Now, this guy right here, this is the definition of equality that we have inside of the point class. So, we can actually replace that with the definition as provided in the point class. In fact, I would argue that it is within your best interest to do so. So the question is, why would you need to do this? Why include point.eq? Why include point.init? Why are we using the point? Why are we making direct reference to the point values methods when we could just copy and paste it or just write it out because it's that simple? There are two reasons, really. Number one, they are not guaranteed to be that simple. You know, when you're actually doing real-world programming, these definitions can get quite lengthy, and it can be quite a lot of work to reproduce them, and when you do so, you're likely to make a transcription error. Even if you're copy-pasting, there will likely be some small things that need to be changed. So, you know, the methods of the point class might be sufficiently large that you don't want to reproduce them. That's number one. Number two, this insulates you against future modifications, right? So you can imagine, let's imagine, for example, we were programming away, and we discovered, after we'd made the colored point class, that we had made an error when we wrote out the EQ class. Some bug or another, right? We made a whoopsie. There is a bug inside of the EQ class. If we had copied and pasted the code from the EQ class of point into the EQ method of point into the equality method of colored point, any errors that we had made, any bugs that we had made, would also have been transferred. That's the downside of copy and paste. Any bugs that you, like, when you copy and paste, you are also copying and pasting bugs. 100% of the time. There is no situation in which a bug will be present inside of the copied text and not present inside of the pasted text, because if that were the case, we could solve all bugs in computing just by copying and pasting our code around, and things would be so much easier. Unfortunately, that's not how life works. So, when you copy and paste the data, you're also copying and pasting the bugs. If you then, subsequently, go in and fix the bug in one place, you have to remember every place you copied that code to and fix it there as well. Now, it's entirely probable that you won't remember all of the places that you copied and pasted that code to, because that's not how your brain works. Unless you have an eidetic memory or something. Which, let's face it, very few of us actually do. So, the preferred solution, then, is to, rather than copy and paste this code, to use the method itself. That way, if there is, in the future, at any point, modifications to this method that, you know, make it better or fix bugs or do anything of the kind, those benefits will be automatically conferred upon the use of that method inside of the derived class. This is basically the same argument for using functions, incidentally. This is almost exactly the same argument for why you would want to use functions. And, of course, methods are functions. So, perhaps it bears repeating. It's important to remember, why we do the things we do. Cool. So anyway, that's how you would go about doing that. So, let's talk about classification. Inheritance in programming languages originates with the classification of objects in the world, for example, in biology, although it turns out that the human brain is just one big classification engine. You know, if I look at this mug, and I do not see each of the individual pieces of this mug that comprise it and make it into a mug. I do not see, this square inch of enameled ceramic right there, right? What I see is a mug. My brain has automatically read in the shape of the object, derived that shape into it's placed this shape inside of a class of shapes that it already recognizes as being things that contain liquid, with which the English word mug has been associated with. There are things that distinguish a mug from a glass, for instance, but both contain liquid. So, one might say that mug and glass both inherit from vessel, or drinking vessel. So, this is what the brain does constantly with everything, right? We even do it with people, right? You have, for example, if I zoom in on this a little bit, human beings are, you can categorize human beings among a very large number of different categories, some of which are rude, so don't. But professions are it's usually not rude to categorize people according to their profession. So, a human might, more specific types of humans might be shopkeepers, artists, or dentists, for instance. One might say that shopkeeper, artist, and dentist all inherit from human. I would say that they inherit from adult human, because generally speaking, we do not assign professions to children in, at least in Canada. I'm not sure about other parts of the world. I think in some cultures there have in the past been societies where you would have a caste system where the child of a blacksmith would be expected to become a blacksmith themselves, etc., etc. It doesn't really, getting into the weeds. So the idea, of artist, you have several types of artists. You have sculptors, painters, potters, digital artists, all of these types of different classifications, right? Of digital artists, you might have an artist who exclusively does, logos for companies, something like that. And of the artists who are of the human artists of graphic design who do logos for companies, you might have ones who do them specifically for car companies. Every time we go down the ladder of classification, we get one step more concrete. We get one step closer to an actual physically existing thing, right? And we get one step more specific. So, the thing about physically existing objects is that you can think of them as being at the very extreme end of a classification tree, right? A physical object exists physically and therefore is hyperspecific, whereas everything above it in the classification hierarchy is a more and more abstract concept, but fundamentally we are dealing with ideas, right? So this is kind of psychology as much as anything else. So the thing about computers, of course, is that nothing really exists physically. Everything exists virtually. So we're kind of operating inside of this hierarchy of inherited classifications without ever having reference to a physical object, right? Within computing, the ideas themselves are the physical objects. because they have been constructed by you. They are specific things. Anyway. So this idea of inheritance derives from the 1960s, and it became a general feature of object-oriented programming languages because it was designed to be useful. So anyway, okay, it's 10:20. We should call it for the 10-minute break. We shall have a break, and we will resume class at 10:30. See you then. Bloody hell, my bloody picture again. There we go. Hi folks, welcome back. I just wanted to show you this interesting thing. I was looking at the analytics for these lecture videos just a little bit to see, you know, if there was anything interesting. And it's interesting because they give you now a graph. Ooh, let me shut myself off. There we go. They give me a graph of like how much people have actually, like, sort of the percent of people who get X far in the video. Now you shouldn't worry too much about the initial peak because a lot of it's like bot activity and stuff. But it's interesting because of the viewers that I've gotten on, I think this one is the from the 18th. Sort of 30% of the views or like 25% of the views I get actually are watching through the lectures, and like by the time I get down here, it's like 15%. But you can see this, like, people are skipping the breaks and stuff like that. It's interesting. It's really cool that you get that kind of analytics these days. But yeah. Anyway, I just thought that was interesting. I thought you guys might be interested in seeing that. Anyway. Cool. Just a little bit of an insight into the life of trying to put videos up on YouTube. The general reception I get is that people like YouTube as a platform for lecture content delivery. So, you know, I'm probably just going to keep using it. I'm not a big fan of Teams. You know why I'm not a big fan of Teams? Because I'm a big fan of fidelity. By which I mean, like, audio-visual fidelity. I know that the streams can, like, get a little fuzzy, you know, and, like, 360p is not the best, but, like, good God, at the very least, the audio quality should be much, much, much higher than you get from Teams. Yeah, I think those gaps, they have to be the break times. Yeah, absolutely. 100%. 100. Which, you know, yeah, it's interesting that actually shows up in viewership, right? Anyway, so, talking about classification. So, in our classification of objects that we were working with before the break, we have object, which of course is the most general thing in Python. Everything inherits from object, whether it wants to or not. We have point, and we have colored point. So point inherits from object, colored point inherits from point. Colored point has inherited everything from everything above it in this hierarchy. So colored point includes everything that's in point and everything that's in object. Anything that point overrides from object is also overridden for colored point. So it kind of has this view backwards through the inheritance hierarchy. So the changes that the classes make along the way are still visible to colored point. So let's talk a little bit about how you can tell what a thing is. So we can tell whether an object is a... I'll do this in the form of assertions. So remember assert statements from last time. If the condition comes out true, then nothing will happen, and we'll see the print statements. So if we assert that the type of P is equal to color point. Oh, we get an attribute error. Point has no... I've got an error. Yes, because I'm comparing things in manners which are not correct. So, there we go. So, this assertion comes out to be true. The type of P is colored point. Notice you can just use the class name here. Assert that the type of Q is equal to point, and assert that the type of P is also equal to point. So on this last one, we get an assertion error. The type of P is not equal to point. This is what one might expect. P, if you actually print the type of P, print type P, you get class main.coloredPoint. So regular point isn't visible, even though it's being inherited from. So this type function is not a test to see if a particular class inherits from another. IsInstance does that. So if we assert, if we want to see if P is inheriting from point, we say assert IsInstance P point. Yes, it is. So IsInstance will tell you if the object that you're testing inherits from a particular class or is that particular class. So if you're needing to know, that's how you can determine it. Cool. Yeah. Yeah, it's not bad, right? The one thing about the YouTube lectures with respect to, with respect to this is that there's a significant lag between when somebody makes a comment and when, like, I see the comments more or less instantaneously, but because of the, buffering or whatever, it takes time for my response to the question to actually show up in the feed, right? It takes anywhere between 15 and 30 seconds. So sometimes up to a minute. Although I've been doing pretty well since I had the people fix my internet. So that's the one thing. So like doing the in-class surveys and that sort of thing, that's less feasible on this particular format. But generally speaking, I think the pluses outweigh the minuses. I think the pros outweigh the cons. Anyway, so so let's talk now about something a little bit different. Multiple inheritance. Related, but different. So, with this color point example, what we're doing is we're taking the idea of a point and we are putting on top of it the idea of a color. Now, it is entirely possible that we may wish to define properties relating to color for things other than points. Think about it this way. When you're in a word processor and you're making your rectangles and you're deciding what color your text should be and all that kind of fun stuff, when you select, if you go sufficiently deep into the dialog options for color, it doesn't matter what you're deciding the color of, you will always kind of end up at this, that screen with all of the color swatches at the bottom and the pane that has the rainbow that's like all the saturations and everything. And you can slide around and select specifically which color you want. that dialog is the same no matter which route you have chosen to get to it, right? It doesn't matter if it's the text that you're choosing the color of, or a text box, or a line, a border. Doesn't matter. Every route will eventually bring you back to that dialog box. All roads lead to Rome. So the color dialog is a property common to everything that can have a color. So we might, in that sense, we might derive a mental concept that the idea of color may be abstracted from all of the things which may have color as a property, right? Long way of saying it, just because points can have color doesn't mean that all of the code that defines how a point define how color works should be restricted to this idea of being associated with points. We can abstract the idea of color. We can produce a new class, color, which inherits from object, which contains all of the definitions related to color. So we can define init self color not self dot color equals color not. Define darken self. Just copy that in. Actually, I could just copy the whole thing in. And def equality, taking self and other, returns this expression here. Then, so now we have a class for color. We may inherit this point, we may inherit this color property, sorry, that's the wrong verbiage. We may use this color class to derive the colored point class by invoking multiple inheritance. So multiple inheritance is exactly what it says on the box. You are inheriting from multiple things at the same time. This list of classes that you can inherit from is, in some ways it looks like an argument list, but, up to this point we have only been inheriting from single classes. You actually can inherit from multiple classes. If you have a comma delimited list, or a comma separated parenthesis delimited list of class names. So you can then color dot init, you can drop in the constructors for all of the subclasses, and you can pull in the equality definition as well. There we go. So this is the idea of multiple inheritance. Classes may inherit from multiple different things, hence multiple inheritance. Let me see if we have any questions. Yep. So, in this way, color can also be inherited by other classes. Reusing code through inheritance contributed to the popularity of object-oriented languages. Code reuse is like the #1 purpose of abstraction in programming languages. So, or at least among object-oriented languages, which are derived primarily from the inherited, or the imperative school. Yeah. So you can imagine, now that the idea of color has been abstracted from this particular example, you might imagine we would want to extend this idea with, if we wanted to add classes for lines, if we wanted to add classes for areas or figures, or, objects in three-dimensional space, all of these things become possible. All of these things can inherit from color, and then we have to do very little work in order for a line to also have a color attribute. Right? Make sense? Hopefully that makes sense. So this kind of bleeds into the idea of an abstract class, and this is another conceptual point. In the middle, we're making a lot of conceptual points about classes. After we get into this, we get into some concrete examples. So, abstract classes. Color in this instance doesn't really make sense to have a color that is color doesn't really exist except as a property of something else, right? The color red, like color is an adjective, is another way of saying it, right? Color describes things. Color is not so much a noun as an adjective. It doesn't exist independent of the physical existence of the thing it's describing. So, in that sense, when we create a class for it in Python, what we're doing is we're creating an abstract class. So, this class, the only purpose that it serves is to serve as a base class for inheritance. It's, in that sense, similar to the object class that is inherited by everything by default. That you wouldn't really instantiate, typically you wouldn't instantiate a general object in Python, right? All it is really is a container for definitions that are being used by other class definitions. So that's what an abstract class is. The purpose is code reuse. The purpose is, making everything nice and pretty with respect to the manner in which your programs are constructed. You wouldn't necessarily instantiate it. Perhaps there's a situation in which you would, but that wasn't the impulse to create it, if that makes sense. So that's what an abstract class is. Are there any questions about that before we move into our practical examples? I'll take a moment here, and if you're good, give me a thumbs up. Give me a thumbs up. Let me know you're still alive out there. Awesome. One guy is listening. Thank you. Thank you for listening. Excellent. Awesome. All right. So let's do some practical examples. So let's make a class for the birthday calendar. So the birthday calendar, in general, the purpose of the birthday calendar is to associate a bunch of names with dates upon which people have birthdays. What we're essentially doing is we're creating a dictionary with some additional functions built in, which provide additional additional functionality. Mostly the purpose of this is to provide a couple of checks. So, like Boolean checks. So, we are given a list of methods that we want to implement. We've got clear, which removes all names from the calendar. Add adds a name and with a date to the calendar. Contains checks to see if the name is in the calendar. And birthday's date returns the set of names with birthdays on that date. This will require a data structure with entries for names and dates. The data structure is shared among the operations. A class allows us to encapsulate operations on shared data structures. So, this is I kind of gave away the idea of what type of data structure we would use to implement this. It's a dictionary, but what this is essentially doing is this is allowing us to again provide a controlled means of access. You know, it might be that we need, like going back to the person example. If we're recording all of our persons using dictionaries in the same way, and if we had written a function that performed a marriage operation given to person dictionaries, that's an excellent candidate to be a method of a class, right? If you have a function which uses a particular data structure which has a particular data policy, both that data structure and the method should be put into a class. The data structure, like the data policy, should be encapsulated. Encapsulation is a if you go on to take more computer science courses, that's a concept that you'll hear a lot about in sort of the middle to upper levels of computer science. The idea of encapsulation is the idea that everything should be contained, right? The purpose of the class is to contain everything that pertains to it. There should be no functions outside of the class that, operate only on objects of that class. That should be a method of the class. Encapsulation. Get everything inside of little packets. Anyway, so let's implement this. I'm just going to comment out my print statements up here. Boop-a-doop-a-doop, boop-a-doop, boop-boop. There we go. All right. Class B-Day. So we're given 4 methods that we want, right? So let me just split this screen. There we go. So we want a clear method. We want an add method. Name date. Contains method. Takes just name. And we want a birthdays method, which takes a date. We know, by default, that all of the methods that are contained in a class take self as the first argument, so let's just slip that in there. And, of course, every class needs a constructor, so we pop an init in there as well. So now we need to decide how we're going to organize our data. We're going to have to decide on our data policy. So I've already said that we would probably be using a dictionary here. The reason for that is that we're relating names to dates and dates to names, right? We're relating strings to strings. We're mapping strings to strings. That's a perfect application for a dictionary. The only question is, what should be the keys and what should be the values? It turns out, by deciding, whether you decide to make the keys or whether you decide to make the names or the dates the keys, that'll change how difficult either contains or birthdays is, right? if you make the dates, the birth dates, the keys of the dictionary, then looking up all of the names associated with a particular date is a simple matter. All you have to do is perform a dictionary lookup, right? All you have to do is index over the dictionary, and you'll find the names. That does complicate add somewhat, though, because that means that each entry in the dictionary points to a structure that contains names rather than just a single thing. In the reverse direction, assuming names are unique, that's sort of a baseline assumption that we're making here, is that people's names will be unique, but their birthdays may not be. That's sort of an assumption underlying this entire structure. If every name is unique, then all we have to do if we make the names the keys of the dictionary, then all they have to do is point to a date. Contains becomes very easy. To check to see if a name is in the dictionary, all we have to do is check the keys. However, finding all of the names with a particular birthday becomes slightly more complicated. So, just because it's the slightly more complicated version overall, I'm going to do the one where the date relates to the person. So the date is the key, the name is the value. So self.d is equal to an empty dictionary. So let's just go through these in order and fill them out. So to clear self.d, there's it's very simple. All you have to do is reassign an empty dictionary to it. An alternative to that would be you could invoke bday.init. So you could reinitialize bday. That would have the same effect. As you can see, all we would be doing here is going there. But again, this eliminates a certain amount of copy pasting, so it's the preferred solution. That way, if there's any additional data that we ever want to add in the future, favorite type of cake, perhaps, anything like a clear operation and a reset operation and an initialization operation, most of the time those are going to be the same gosh darned thing. So this makes sense to do. All right, so how do we add something then? Well, in the same way that we had to check things before we added them when we were doing memoization a few weeks ago, in order to add a name to the dictionary, given that the dates are the keys, we need to first check to see if the key is in use. So, if date is in self.d, remember that automatically searches the keys, then self.d at date is equal to self.d at date plus, or concatenate, we'll just store them in the lists. I know it's like kind of expecting a set here. Well, now we'll do lists. We are concatenating the name to the list that is stored at self.date, or self.d at date. Otherwise, so if date is not in the dictionary, self.d at date is equal to a list containing name. There we go. Easy peasy. If it doesn't exist, create it. If it does exist, add to it. So, I'm going to do birthdays first, I think, just because that one's easy. So, birthdays returns the set of names with birthday on that particular date. So, so we're returning self.d at date, and if they want a set, then by golly, they'll get a set. There we go. Easy peasy. And now contains. So the set of names with... so contains checks if a name is in the calendar. So this is, you know, slightly more complicated, but not that much more complicated. We have a dictionary. We need to check the values of the dictionary, which are sets of data structures, to see if a particular name is contained anywhere. So, for date in self.d, for n in self.d at date, if n is equal to name, return true. And if you get through all of that without having returned true, you return place, by which I mean false. There we go. Excellent. And that's it. That's the entire thing. So let's just test this a little bit, see if it works. So calendar is equal to bday. Doesn't take anything to initialize. Calendar.add John Doe, birthday 01/01/1970. Cal.add Benjamin Franklin 01/01/1970. Cal.add Gunther the Penguin 05/09/1987. So we can see what's going on inside of the data structure because it's a public data structure. We're going to discuss the difference between public and private ones towards the end of this lecture. We can just view it by printing cal.d, but we can also say, let's say test one. Let's see whether let's see the calendar dot birthdays on 01/01/1970 and calendar dot birthdays, or no, contains this guy right here. And let's also check to make sure that clear works. So cal.clear print cal.d. There we go. So we've got some data. So here's our dictionary. Notice we have dates which point to lists of names. This is correct. The data is being entered correctly. Test 1, we have a set containing Benjamin Franklin and John Doe as names. Test 2 comes out true because this is contained. But, of course, if we modify the, if we make it Gunther instead of Gunther, then test 2 comes out false, which is correct. Okay, so this is actually an important point. I made a mistake here. Calendar.clear. This is like just me stating the name of a method. If you actually want a method to execute, you must provide the two parentheses. even if you're providing no arguments, the 2 parentheses indicate that the method actually is to be executed. So otherwise, it won't execute. But if you include those, then it clears the dictionary. So there you go. Ta-da! Birthday calendar. Let me see. I love it. I love it. So let's see how we did, relative to the slides, that is. So, init, the same. Clear, the same. They've included doc strings, which I didn't, because I'm a naughty boy. So, add. So, you see in this version of the birthday calendar, name is being used as the key rather than date. So, self.calendar@.name is equal to date. You don't have to worry about checking to see if the name is already in the dictionary, because we're assuming, even though it's not stated, that all names are unique, even though they're not, technically speaking. Although it's a better assumption to assume that all names are unique than to assume all dates are unique, because there are only 365/66 dates, whereas there is a lot more names than that, but it's still not a good assumption to assume that all names are unique. So contains, that all we have to do to check to see if a name is in the dictionary is to, it's essentially the same operation as, where was it? Right here. As this guy, except instead of using a lookup, we're using the in operator. And for birthdays, to return, or that's contains. So for birthdays in this case, returns a set of names with birthdays on the date, n is equal to an empty set. For e in self.calendar, if self.calendar@e is equal to the date, then you add that to the set and then return it. And of course, they've got string conversion, which was not asked for, so I didn't include it. There we go. Cool. So that's the birthday calendar. Any questions about that? Give you a moment. Again, if you are good, give me a thumbs up. Yeah, the other thing about YouTube that I like versus Teams is, I don't know why, I feel like it's easier to get at archival lectures. Like, I know, Microsoft Stream does exist. It just, actually getting at it is, roundabout. I think YouTube is more convenient. It's, right there, I can set up an automatic playlist that automatically adds the lectures to a playlist and stuff like that. Anyway. Awesome. Cool. So, let's talk about yet another example. Let's do a mean calculator. So this is a calculator which, it's not a mean calculator in the sense that it offers verbal abuse at the same time as calculating numbers for you. This is a mean calculator in the sense that it calculates arithmetic mean. So this is a statistical thing. So we want to design a calculator for arithmetic mean with the following 2 operations. 1, add. 2, mean. You can add and you can mean. The mean should account for the same number being added multiple times. As one might expect. So, let's make a class. Class mean mcalc inherits from object, that is to say, almost nothing. Define init, because you always need init. Take self, not slef. Self. Def. Add. N. Def. Add. No. Mean. Nothing. Except slef. I mean self. Self. There we go. Self. So far so simple. So we have to decide how we're going to store our data. What is our data policy going to be with respect to the mean calculator? How shall we store the data? Well, it would be reasonably simple to just dump everything into a list, right? Dump it all into a dynamically allocated data structure, and everything's hunky-dory. So, self.list is equal to an empty list. If we add n to the list, that's easy. It's self.list is equal to self.list plus concatenate, n, which must be in its own list. You could also do self.l.append n. There we go. And if we are to calculate the mean, we must return self.l, self.l, sum of self.l divided by the length of self.l. Because, of course, the length is the number of objects that we put into the mean calculator, so that is the size of that's the number of things we're calculating the mean over. Anyway, so let's test this out. Capital M is equal to mcalc. M.add 1, M.add 2, M.add 7, M.add 3. Print M.mean. Attribute error. All right. It's not liking my use of append for some reason. I'm not sure why. Oh, yeah, I know why. It's like dot append n. There we go. Right? Yeah, there we go. So the average then is 3.25. Just going to make this into an actual mean calculator. So, it not only calculates the mean, it also insults you. The average is 3.25. Dummy. There we go. So, or I guess our meme is fool, isn't it? There we go. So far so good. Let's see how we did in comparison to the slides. So, yep, pretty much exactly the same. So, here's the thing, though. We're actually using more memory than we need to. There are two approaches that you can take to calculating the mean. One is to keep all of the data that you've ever been given somewhere inside of the class. The other is to simply maintain a couple of variables which keep track of only that data that is relevant to calculating the mean. Now, there are advantages and disadvantages to this. The advantage is that you use less memory. That could be quite the advantage, especially if you're working on a memory-limited application. If any of you go on to program microcontrollers or Internet of Things type applications. These types of applications are, generally speaking, pretty memory limited. Memory chips can be expensive, and the more memory that you have on a mass-manufactured computer chip, the more that chip is going to cost. So the manufacturing incentive is to use as little memory as is humanly possible to implement whatever that electronic device you want to implement is. So, you know, there are applications in which you want to crunch memory at this level. The other option is, like, if this thing were running for a very long period of time and accumulating millions and millions of entries, that's another reason you might want to, you know, restrict the amount of memory it uses. The disadvantage is if you ever want to expand the functionality of this class to be able to calculate things other than mean, which is entirely possible. For example, if you wanted to calculate median or mode, or if you wanted to calculate standard deviation, all of those statistical calculations require consistent access to the actual members of the data. There might be ways of doing as-you-go calculations for those things, but certainly not for mode. I don't think you'd get away with it for mode. So if you wanted to expand this with mode, you would need to know all of the history. So if you don't keep the history, then, you know, that would be a problem. But let's implement this again. So class. mcalc2. Some of this I can just copy over. I'm just gonna... So, self.sum is equal to 0. Self.n, or self. What do you want to call them? Size? Or just call it S and C. Count. It's equal to 0. When we add something, self.s plus equals n, and self.count plus equals 1, right? So s is a running sum of all of the things that have been added to the class. Count is a running count of all of the times add has been called, which is the same thing as the number of elements that have been added. So rather than calling sum and length here, all we have to do is say self.sum divided by self.c. And if we execute, if we change this to mean calc2, there we go. Precisely the same functionality. However, I would say in both cases, I just realized this, you might want to guard against a certain unexpected problem. So the way that this has been formulated, if you call mean on a newly created mean calculator that has not had anything added to it yet, you're going to run into a zero division error, right? Because this would be 0, and it would be a zero division error. So, except zero division error, print, I was kind of kidding before about you being a fool, but you really are one, aren't you? So this is a really mean calculator. So that way, if m2 is equal to mcalc, and we ask for m2.mean, we don't run into a zero division error that would crash our program. So this is a safe mean calculator. Cool. So, There we go. So between these two additions, right? This is kind of a dumb question, so I'm going to answer it. So the question is, if only add and mean are used, can mean calculator 1 and mean calculator 2 be distinguished? And the answer to that question depends on what you mean by distinguished. From the perspective of the programmer, there is no way to tell the difference between mean calculator 1 and mean calculator 2. That is, from the perspective purely of someone who is trying to use these classes to perform stuff, to do stuff. Clever students every year say, well, yes, but you could tell the difference by looking at the memory consumption, right? Or even the runtime, or, because the thing about mean calculator 2, which makes it even more efficient than mean calculator 1, is because you aren't keeping the track of this data structure. When it comes time for you to calculate the sum, that's a big O that's a constant time operation, because all you have to do is look up a variable, whereas calculating the sum of a list takes as many. The time it takes to calculate a sum is proportional to the size of the list, so that's big O n, right? So here, mean calculator 1 has a big O n mean calculation and uses big O of n memory, whereas mean calculator 2 has constant time for both of those. So, like constant time mean calculation and constant time, or constant memory, so long as you don't exceed integer limits. So this is really a better algorithm altogether, so long as you don't need to expand it. But anyway, so from the perspective of the programmer, right, the interfaces are precisely the same, right? The input to add is the same in both cases. The thing that the mean method returns is the same in both cases. The programmer does not need to know the manner in which the data is being stored, and they do not need to care about the manner in which the data is being stored. The manner in which the data is being stored has been abstracted away from the programmer, so they don't have to worry about it. That's extremely useful. So this is getting back into the idea of black box, modular black box design, right? Except now, we're able to put data itself into the black boxes. We don't have to worry just about functions. We can't. This methodology does not apply exclusively to functions. We can also stuff data into these black boxes. And classes are how you do that when you want that data to be persistent. Anyway, should probably have our second break. Yes, sirree. We will resume class at 11:33. Thank you very much. Maybe. Yes, I think I am. Oh, we'll see. Always have to check these things. I've been burned once too many times. Good. Excellent. Cool. So, hope everybody had a good 10 minutes. So, yes, we were talking about mean calculator. So, in general, functions provide algorithmic abstraction. They allow you to abstract procedures, right? Classes provide data abstraction, while at the same time providing algorithmic abstraction. Classes can be used without needing to know the details of the data structures that they implement. The documentation refers to abstract data structures that may not be present in the implementation. So, just because the documentation for a class says that it does a particular thing, well, if it's good, it actually does, but you shouldn't worry about the details of the implementation. You should worry strictly about the inputs and the outputs. It allows you to simplify your view of anything that's contained in a class to, how do I use the methods, right? And now that we've covered classes, the next couple of topics that we're going to have in this course use classes, as you might expect. In one case to do file I/O, that is, file input and output. That is, we're going to learn how to read and write files. And learning to read and write files is primarily a method of learning A, which libraries to use, B, which classes to instantiate from them, and C, which methods accomplish the thing you want to accomplish. So there you go. So, this is all well and good, but we can provide extra layers of protection. Hiding methods and members. Data abstraction of classes assumes that attributes are not manipulated from outside the class. But nothing actually prevents outside functions from being accessed. Nothing prevents outside functions from accessing and modifying the contents of member variables. In Python, this can lead to an inconsistent state in Python. If you prefix a member by the double underscore in Python, the member will be private. In quotation marks, because this is Python. I'm just kidding. Ragging on Python a little bit too much. Python will prevent any code outside the class from accessing private members. So, Python is a little bit tricky with respect to this. We're going to be getting into the weeds a little bit here. But, so, let me explain first what private membership is and, like, why anybody would ever need it. So, while it is true that the methods of this function provide a means of access to the data inside, it is rarely going to be the case that you want to completely divulge everything that's in a class to every possible user. In software engineering, we have a very specific idea. We have a design principle called the principle of least privilege. Right? The principle of least privilege. The idea with the principle of least privilege is that everything and everybody should be given only that level of permission which is necessary to perform the function they need to perform. So this is a very good principle. it governs all kinds of ideas, like if we have any Windows users out there in the crowd, you know how Windows user account control bothers you to specifically permit an application which is installing software to actually operate? It's like, are you sure you want to run this executable? Are you sure you want to do this? Are you sure you want to do that? Blah, 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 blah. No, 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 no. You can turn it off, by the way. You can turn off user account control. At least you could in Windows 8. I'm not sure if you can in Windows 10. Probably there's a way to do it. But essentially, that's because there's a difference between your level of permission as the user and administrator privileges. Administrator privileges give you the ability to do more things, like install programs or modify the operating system, stuff like that. The reason that user account control exists is if a malicious program gets hold of your user account, which is entirely possible, entirely probable, in fact, the damage it can do to your system is limited by the fact that it can't do certain things without your explicit permission. So the thing about user account control is if a virus tries to install stuff on your software, install stuff on your computer, basically you would get a give this program permission ? Prompt that you didn't ask for, and therefore you would say no, and that would prevent it, hypothetically speaking. Of course, there are always ways around this, but it does exclude a certain number of like account permission-based attacks. It works more or less the same way in Linux, except in Linux and Unix like systems, you have instead of administrator, you have a concept of super user. So the super user can do anything. You can temporarily give yourself super user privileges, and using the sudo command, sudo super user do. You can also put yourself in super user mode by pressing SU. It requires you to enter your password, but once you've entered your password, it doesn't bother you anymore about it, and it just does the thing that you want to do. You know, if you try to do certain stuff, you'll get a permission denied message, and if the way you get around that is by invoking superuser. But anyway, so that's the principle of least privilege as applied to operating systems. When you apply the principle of least privilege with classes, what you essentially want to do is you want to restrict the user from being able to muck around with your data structures. You know, the whole point of providing methods is that this is the way you interact with me. You know, you can't just grab the list that I'm using and turn it into a tuple and expect me to still want it, you know? Like, you know, someone could come into your mean calculator, turn your list into a string, and, you know, scarper into the distance laughing at you, and then your program would be broken. More likely what would happen is you'd get a bug report saying something like, your program doesn't work, and it's like, well, you're using it wrong, you know? So the way that you get around this is by making things private. Private members are only accessible within the class itself. So the members of the class have access to them, but anybody outside this class does not. And this can be very useful. Python has the worst possible way of implementing this, which is that every single instance of a variable that you want to make private must have a double underscore before it. In better programming languages, you have you can just designate with a keyword that a member is private or public at the time of its creation. Once it doesn't get appended to the bloody name of the bloody thing, so you don't have to repeat it everywhere it occurs, because that's moronic. I don't know why Python decided to do it this way, but anyway. So, anyway, we'll compare two things here. So I should call this a mean calculator 1 and 2. So this is M1, 2, 2, 2, 2, 2, M2, M1.add 7, print M1.s, print M1.c, or wait, M1 doesn't have S and C, it just has L. Never mind. There we go. Print M2.s, print M2.c. So, we get 7. 7, we can view 7, right? However, when we try to access M2.s, we get attribute error. mcalc2 object has no attribute s. That's true. You can't even access it by putting the double underscore in front. So, the thing that Python does with this is it pretends that the attribute doesn't exist, right? It doesn't give you an error like, you don't have permission to access that. It's like, I haven't ever heard of an S attribute. Have you ever heard of an S attribute? It's like, yeah. So it pretends it doesn't exist. Which means that the only way of getting at S is by using the methods that we defined to access S. So we've locked people out of being able to modify things inside of the class to some degree, which is good, because that means that we can be more sure that people won't, take it upon themselves to perform all kinds of crazy manipulations on our data behind our backs and in manners we did not intend. Let me see if we have any questions, comments. No? Okay. Good. So yeah, that's the idea of private members in general. So incidentally, one interesting corollary of this, which is a Python thing, is you can actually create... I don't recommend doing this. This is a stupid thing to do. But you can actually create variables in classes that you're not in. So if I just do m2.s is equal to 5, and then I access it, I get 5. So what's essentially happening here is I can go into the class definition and add an attribute to it externally to the class. And, I think there's a way of shutting this off, which is complicated, but it's dumb. This is stupid, and I don't know why Python does it. So, yeah. It just confuses things. So, we have a little bit of a thinky bit before we close off our discussion of classes. So, this is a scene. This is box art, I believe, from popular video game franchise Super Mario Brothers. I believe this is the new Super Mario Brothers U. No, it's new Super. Well, maybe it is the Wii U one. Maybe it's either the Wii U one or the Wii one. One of the two of them. I forget which one Yoshi was in. But anyway, so video games are software entities, and as software entities, many of them are made using object-oriented programming languages. So, video games can often be broke into classes and objects. I do a little bit of that sort of thing myself on the side sometimes, as a kind of a hobby type thing. And when I do game development, I do it in Unity. Unity uses C# as its scripting language. C# is a derivation of C++ and Java, which are both derivations of C in the same way that Python is a derivation of C. So we're still operating in roughly the same paradigm. We're still in the object-oriented paradigm. So if we look at this in the chat, tell me some classes that you would imagine are being used to implement the game objects that you see on the screen here. Put them in the chat, as many as you like. Go, go, go. Go, Bitbusters. Question mark box. Yep, that's one. Yes. Where's everybody else? Has everybody tuned out? Do the coins count? Yes! So coins would be objects, right? Coins would certainly be objects. I would say, personally, that coins and mushrooms would both be inheriting from a pickup item class, right? There are several things in a Mario game which, you pick up to, modify the game state in some manner. Coins are pickups. Mushrooms are pickups. The fire flower is a pickup. That little bush berry that Yoshi eats, that's a pickup. Each one of these modifies some internal state of something else, but, in general, those would be things. The enemies, yes. So, enemies as a class would be things which, on collision with player character cause player character's damage method to be invoked, right? Except, there are certain interactions where, certain relative interactions where a player is not injured. Jumping on top of a Goomba is different from being hit from the side, and a piranha plant cannot be touched safely. So, Goombas and Paragoombas would both be inheriting from enemy, and Paragoomba would inherit from Goomba with modifications for the wings. In fact, the wing sprite itself, or the wing model, the model that's used to graphically represent wings in the game, those would be objects. That would be a separate object that would be inherited by Paragoomba, so that you could apply it to the model and thereby change the appearance of the Goomba, which is necessary from a ludic perspective to indicate it as having different behavior from the regular Goomba. Not sure what they're called, but the things they're flying on. Yoshis, yes. I believe this is more of a jump animation than a fly animation. But yes, tunnel. Yeah, so the warp pipes would also be, physics interactable objects that sort of warp you from one point in the level to another. Bricks are objects in the game which have a particular interaction if interacted with in a particular way, but also have physics collision properties. Yes, I would actually classify this like Yoshi, although Yoshi is kind of it's a little bit mean, but I don't believe him to be a character. He's more like, I don't know what, in terms of code, distinguishes Yoshi as an entity from something like the propeller hat or the fire flower pickup. Like, Yoshi is a pickup, right? You have to jump on him. You have to interact with him in a particular way to acquire him, but Yoshi is a pickup, which would put him closer to a mushroom or a coin. But yeah, so in general, you could even go one step further with respect to the character-enemy distinction, and say that both player characters and enemies have the same sorts of physics interactions, and therefore likely inherit the physics engine from some base class somewhere. Cool. So, here's one possible hierarchy of things that you could have in a Mario level. The level itself, the arrangement of blocks, presumably the arrangement of blocks is stored somewhere in memory that would need to be called out. Characters are either playable or non-playable. Non-playable ones include Goomba and Koopa Troopa. Playable characters would include Mario, Toad, Other Toad, and Green Mario. Widgets include things like brick blocks, question mark blocks, music note blocks, the one-way platforms, I would say. One-way platforms are also a type of block, I would say. Warp pipes would be a type of block. Yep. So, with respect to the classes that are in here, the types of properties that these classes would have are, in the case of a playable character, say your Marios, are things like what is the name of the character, is the character in big state, has the character a feather, although I do not believe that feathers are in that one, so whoever wrote this is thinking about Super Mario World on the SNES. Number of coins acquired, X and Y coordinate in space, and some methods. Move to, well, that's not really how Mario moves. Mario moves on a momentum system, so it's more like received controller inputs map to momentum, and the momentum itself, as a subroutine, updates the character's position, right? Collect coin is definitely a thing. Draw on screen, that's a very important one. So, although draw on screen on in any modern game engine, draw on screen would be a thing that the game engine itself would handle. Question mark block, that would be, so question mark would inherit from block. We would have such things as X and Y coordinates, contents, whether or not the block has been used. Smash would have different behavior depending on what type of block it was, and of course, draw on screen. So there you go. We have discussed classes. If you have any questions about any of that, any questions about anything in particular, I will give you guys a moment to ask them now while I load up our next topic, which we have a few minutes to be able to cover. There we go. I probably shouldn't have closed that. Okay. I'm sinking lower as things go on. There. So, good. So much for classes. So much for pathos. So let's talk about files then. We got 20 minutes left. We can talk about files. So, and now for something completely different. So, files then. You should know what a file is already, in theory. A file is anything that's stored on your computer's hard disk. File systems are the manner in which data is stored on hard disks. We are talking here about ROM, or read-only memory. Read-only memory does not mean that you can't write to it. It's just, well, it used to mean that, but these days, you know, you certainly can modify files, and we're going to learn how to do so. So, for me, in Linux, ls lists all of the files in a particular directory. And if I cat something like topic1.py, I get a listing of the contents of that file. So in general, files are typically, it depends on what the file format is, but the files that we'll be dealing with here are stored in character formats directly. So we're going to be working with what are called plain text files. A plain text file is a file where the contents of the file are specifically encoded as characters, right? If you, let me see if I've got a PDF around here that I can show you. If you, to MP3, sure. If you take a look at something like a PDF document, PDFs are not stored in plain text. They are encoded. So if you were to try to view the contents of a PDF in the same way that I just viewed the contents of a plain text file, you will get a whole bunch of garbage. This is what a PDF looks like in terms of the actual... Like, if you were to take a PDF, take all of the bits that comprise the PDF, and display them as characters, you would get something that looks like this. So, yeah, we're not going to worry about those. Generally speaking, if you're looking at this, what your brain should say to you is, I probably need a program to read this, which is going to be true. So, we've already talked about input and print fairly, like quite a bit. I'm not going to cover them in great detail here because we've already used them quite a bit, and you should have a fairly good idea of what they do. But we're going to dig a little deeper into them. So, the way that print actually prints stuff to the actual terminal here, close that, open a new one, there we go, is what this terminal is displaying for me is the contents of a file which is shared. It's an operating system file, so it's shared among many processes, called standard output. Standard output is, you can think of standard output as being a buffer, so it stores characters that need to be put into the display terminal. And the manner in which... sorry, just give me a second, guys. we go. Sounds like it's feeding time for the little munchkin. When you print something, you're not actually, like, the thing that it's doing under the hood. What print is doing under the hood is it's sending a command to the operating system saying, I would like these characters placed into standard output, please. And the operating system says, thank you for this input. We will put these characters into standard output, and then standard output is cleared on a regular sort of a different operating system process is constantly looking at standard output to see if anybody's put anything in there, and when it finds something in there, it places it in a display, right? So that's what print actually does. It puts characters into standard output in order that they might be displayed by other processes in the operating system. What input is doing is it's reading from a different standard buffer. It's reading from standard input. Standard input is basically the same thing, except rather than displaying stuff on the on your computer, it is reading keystrokes, right? So anytime you press any key on your keyboard, that keystroke is logged and placed into standard input. Programs have to request to read standard input specifically. So it's not like an automatically shunting data to display system like with standard output. With standard input, a program has to actually request that the keystroke be has to request keystrokes. So this is one of these interesting things you used to see in like really old computers. It happens a little bit these days, but in old computers, you could type faster than the keystrokes would be taken up if the computer was busy working on other things. So you could type faster than the letters would display on the screen, and that's why it's like it would fill up standard input, and then it would be processing other things, and it would be like, oh shoot, I need to do standard input, and then it would put it it would process standard input, and you would see your words appear on your text document or whatever. A similar process goes on these days. If your computer is a little bit old and a little bit slow, like mine is, particularly when you're starting your computer up, if you load up a web browser while all of your operating system functions are still loading, it takes some time, and it takes long enough that you're tempted to relaunch it, thinking that the computer didn't get the message the first time, and then so you click again, and you click again, and you click, and then once everything does load, you get 12 instances of your internet browser open. And so it's a similar process. Those mouse clicks are logged and then dealt with later. Dealt with when the computer has the resources available to do so. So that's why pressing the button 10 million times does not work. Press it once, wait for it to execute. Congratulations, you are now a computer genius. So, standard input and output. Printing to the screen and reading from the user are modeled by special files called standard output and standard input. In command line scripts, we can redirect standard input and standard output to files. However, this is outside of the scope of this course. If you want to learn how to do that sort of thing, I recommend taking 1XC3 with me in the summer semester. We're starting that up in June. Immediately upon termination of this course, I am teaching 1XC3, which deals with this kind of stuff. So if you're interested, take that course. We're also going to be learning C programming. So we are going to learn the language that I keep saying is better than Python, and then you can make your own determination about whether it's really better. So yeah, so when you call input, prompt is written to standard output, and a line is read from standard input and returned as a string. And print just puts something in standard output to be printed. So, let's talk about files. So why do I talk about all of this business with respect to standard output and standard input and all that jazz? Because the procedure for operating on files is reasonably similar to the procedure for operating on standard input and standard output, with two main differences. Number one, files must be opened and closed. And number two, only one program may access a file at a time. With standard output and standard input, you know, they're system files, so lots of fingers are in those particular pies at any given time. But with files that you're reading from the regular file system, only one process is permitted to have access to it at a time. That's why it's important to close it. Opening the file tells the operating system, look, I'm working on this file, don't bother me. Don't let anybody else touch it, please. Closing the file says to the operating system, look, okay, I'm done what I need to do with that file. I am releasing my hold on it. You may now use it for other purposes. Aside from that, there's just the middle bit, which is the actual reading to or writing from the file, which is very similar to using the print or input methods. In fact, you can even use print directly to write into files using one of the options on print, but we're probably not going to be doing that very much. So yeah. So, the procedure. Number one, open the file for reading. Obtain the file handle. The file handle is an object which has methods. Read or write one or more lines to or from a file by referring to its file handle. These are methods of the file handle. And then close the file. So, here is our very simple example of file I/O. Get it? Topic 9.py. So, fh is equal to open myfile.txt. I'm going to need a myfile.txt. Actually, you know what? We'll use an existing file. Topic 1.py. There we go. So, the open function opens a file. You must specify as the first argument the name of the file to be opened, and then what mode you want to open it in. Specifying R puts it in read mode. So you've got read mode, you've got write mode, you've got a bunch of other modes which are fancier, but read and write are the only ones you need to be concerned about for this course. This operation returns a file handle. The file handle has all of the methods that we need to interact with the file. So, string is equal to fh.read. So we are reading the contents of the file. fh.close. Always close a file once you're finished with it. And then we can print the file. Oop. Gotta be a string. A file contains. And then we can print the contents S. Oh, Python 3 topic 9.py. So the file contains, and then there is the contents of the file. Beautiful. So because this is a Because this is now in string format in Python, we can do anything we want with it that we can do with a string. So if we wanted to, we could do something like print s dot split on new line character. This gives us a list of all of the lines, contents of all of the lines in the file. All of the lines in the file as a delimited list. We could say s is equal to s dot split n. We could say s for character in s, s2 is equal to the empty string. If c does not equal the tab character, s2 plus equals this character, and then we modify that, there we go. Oh, include that, there we go. Removes all tab characters from the file. Without the split, that looks like this. All tabs have been removed. This is, of course, terrible if you're working in Python because the tabs are important, but you can see how you can do anything you want to a file once you've got it in your hot little mitts. Let me see if we have any questions. Yeah. So, yeah, once you've read the file contents in, it's just a string, and you can do anything you want with it. We've got a few functions, so let's just review the functions that we're using here. Open opens file name and returns the file object fh. Mode specifies the mode. R is for reading, W is for writing, A is for appending. So appending a file does the same thing as appending a list. That means you're just adding stuff to the end of it. fh.read reads the entire file into memory and stores it as returns it as a string. fh.readLine reads the next line into memory and returns it as a string. So it goes line by line, and you have to call readLine multiple times each time you want to read the next line. This is kind of similar to reading inputs out of standard input. fh.close closes the file and frees the resources associated with the file object. Ba-da-ba-da! So, reading an entire file into the string using with. So this is fine, but we can go one step. There's one more thing we can add, which makes things easier. You might say, Mr. Professor, sounds like kind of a pain to have to remember to close the file every time. I'm a Python programmer, and therefore I don't like doing work. Terrible. I'm sorry. My apologies to all the Python programmers in the world. You can use a with clause, or a with statement, which we haven't actually discussed yet, but it's kind of one of those built-in things like a for loop, which has particular meanings depending on how you use it. In our case, it will deallocate the file handle automatically once you get outside of the context of the with statement. With statements are used to establish locality. So with x as y means for this block we have a variable x which has an initial value of y. Outside of this block it doesn't exist. So it's like a way of establishing a local variable without using a function or a class. In Python, the file handle is automatically closed once execution reaches the end of the with block. So this is just a fun, easy way of not having to remember to use a close statement. You can see it does the exact same thing. So yeah, I guess that's it. If there are any questions, please put them in the chat now. I would appreciate thumbs up if there are no questions. And yeah, I guess we'll continue next week. Thank you all less than 20 of you who are sticking with the lectures. It's really sad to be lecturing to an empty room, you know? So I appreciate it, you guys preventing it from being an empty room. All right. I'll let you guys go. I'll let you guys get to your tutorials. Maybe nuke yourself some pizza pops in the meantime. Take her easy, folks.